Hi, everybody. So this is lecture 22. This is March 18th. We're discussing section 8.3. Again, we discussed 8.3 on Monday. Remember, last week we discussed, well, not last week. Before the break, we had section 8.1, which was about sequences, and section 8.2 was series. So you add up the terms of a sequence, and we just had the most basic examples and a couple of, an introduction to the idea of when a series converges or not. Section 8.3 is more ways of determining if a series converges or not. So we have the integral test and comparison tests. So we were discussing 8.3 on Monday. So I'm going to start with conceptual questions. Now, conceptual questions mean just testing your understanding of concepts. They typically don't have computations, which might make them seem easy, but they're actually usually harder because they're testing your deeper understanding of underlying concepts. So here's an example, example 1 of a conceptual question. Suppose AN and BN are series. So those are series such that, with positive terms. Such that, and also it is known that Bn converges. So I'm going to ask you 2 questions here, and hold your answers. I'm going to call on people. So A. If AN is greater than BN for all n, what can be said about the series AN? And why? That's one question. And then leave some space. You don't have to write it down because we're going to get to it, but I'm just going to tell you where we're going. If AN is less than BN for all n, again, you don't need to write this down because we're going to get to it, but I just want you to see what's coming. What can be said about the series AN? And why? All right, let's go back to this question. Suppose series Bn converges, and series AN has the property that all the terms of series A are greater than the corresponding series terms of series B. What can you say about series A? Annika? But, okay, bounded below by Bn. Can you say anything more about that? Can you say that series A converges?
So Bn converges, right?
Yeah. Well, Annika's thinking, you all can keep thinking too, because just because Annika's thinking doesn't mean you have to stop. So, can you say that series AN converges? Can you see that? Jace, you're shaking your head.
If AN is greater than BN, then we don't have enough information to know.
Right. So So Jace is getting at we don't have enough information to know. Now, if you want to explain this to somebody who doesn't get why, just saying, well, we don't know, doesn't sort of bring them in on the story, So can we think of a richer explanation why we don't know? Yeah.
We don't know that BN is the largest possible converging series, so just because something is bigger than that, it could still converge.
Right. So it'd be great if we had some examples. We can't say whether this series converges or diverges. So it'd be nice to have an example where a series AN has that property and converges, and one where series AN has that property and diverges. So for example, observe that for n greater than or equal to 1, we know this. Right? So we've got that string of inequalities. If I take a number here, this one's less than or equal to, but from then on there's strict inequalities. So let's consider the reciprocals. 1 is greater than or equal to 1 over n, which is strictly greater than n squared, which is strictly greater than n cubed.
1 over?
Yeah. 1 over those. So consider these series. I'm going to have two different series that I call AN. So we have this series, or this sequence BN, and so we have this converging. This is a P series with P equals 3, which is greater than 1. Now let's look at this sequence. This sequence causes this series. Does that converge or diverge? Converges, because it's a P series with P greater than 1. Now what about this sequence, 1 over n? It gives rise to this series. Does that converge or diverge? Diverges, because it's a P series with P equals 1. So notice, both of these series have the property that AN is greater than BN. So 1 over n squared is greater than 1 over n cubed. This series converge. 1 over n is greater than 1 over n cubed. This series diverge. So you really can't say. So it's important to distinguish between saying, I can't say because I don't know, versus we can't say because it could be different possibilities. Here's an example of these different possibilities. So it's always really good to be able to illustrate what you mean when you say you can't say anything. Jace kind of got at this a while ago. Okay, now we've arrived at question B. Suppose it's known still that series BN converges, but this time it's known that AN is less than BN. What can be said about this series AN and why? Who can help me there? Yeah. Now we're in section 8.3. In section 8.3, we, as I mentioned a while ago, we have these tests for convergence. So do any of those tests help us in this case? Huh?
Comparison test?
Yeah. Let's look at the comparison test. So AN converges by the comparison test. So let's pull that up. So yesterday in your recitation, I think I have my lightsaber. Oh no, somebody broke my lightsaber. If you have sequences of positive terms, if we're looking at case I, if AN is less than or equal to BN and the series BN converges, then the series AN also converges. Great. That's the first conceptual question. So again, no computations here, but it's really good to be able to articulate a good example. Example 2. Distinguish between this series and this series. So the first series is the sum from 1 to infinity of n to the b, and the second series is the sum from 1 to infinity of b to the n. So the question is, what do you call these things, and for what values of b do they converge? What do you call them, and for what values of b do they converge? So who can help me out here? What do you call this baby? Got one hand up. I'd like to get some more hands in the air. Marcy, we haven't heard from you.
The geometric series?
Kenzie, what do you have to add to that?
I would describe it as a p-series.
What do you make of Marcy's comment about geometric series, though? Annika.
The second one would be a geometric series.
The second one is geometric series. So Kenzie, what did you say again about the first one?
The first one is a p-series.
Yeah.
Which will converge with the
Shh, oh, wait. stop there. Going to make somebody else weigh in. The first series so this thing can be rewritten. This is this series is this series, the sum from 1 to infinity of 1 over n to the minus b. So that gives you an idea of why, where Kenzie got called this a p series. So this is this converges. So somebody else weigh in. When does a p series converge? Waiting for some more hands here. Sam? Oh, Mary?
It's greater than 1.
Yeah, and when the exponent is greater than 1. Converges when minus b is greater than 1. Whatever that exponent is, it's got to be a number greater than 1 for this to converge. Remember a while ago, this diverges, this converges, this converges. Well, let's work on this. If b is greater than 1, negative b is greater than 1, let's multiply everything in that inequality by the number negative 1. So then I get b on this side and I get negative 1, but I have to reverse the inequality. So b has to be a number less than negative 1. So if this is the number minus 3, then this series converges. If this is the number minus 2, this series converges. If this is the number minus 1, this series does not converge, because we'd be looking at those three cases. Okay, what about the other? I'm going to let Marcy take this one. So Marcy, this if we expand this, this is b plus b squared plus b cubed plus b to the n plus, and keeps going. Marcy, when does that converge?
It converges when n is equal to anything between -1 and 1.
When r is the base. So this converges. So this, I'm going to call. We didn't name this. This is a geometric series with r equals b. Here I should have said p series with p equals minus b. All right, so Marcy, say it again.
Whenever r is greater than -1 or less than or equal to 1.
And less than, yeah. So converges when b is between -1 and 1, not inclusive. Okay, so again, that was a conceptual question. No computation, but you have to be on your feet. I mean, that's meeting part 1. Meeting part 2 is harder examples. Dun, dun, dun. Now, this sometimes happens. I start making lovely notes, and then get them all done and realize I've got too much stuff. So the problem that I'm going to do is a whole damn page. And so that's example 3. I had example 4 in here, and its solution is almost a whole page. So it's colored red, which means they decided that's too much to do in a lecture, two examples that long. But you should know that your homework includes some really tough examples, as hard as like those integration by parts problems that we started the semester with. And also this red one that I decided I'm not going to do in class today, it's really a cool problem, but it just, you can't do all the problems. So work on, these are both similar to homework problems. Work on your homework if you have questions. What I have in my notes is, don't do this in class, leave for curious students in office hours. So, work on these problems and keep in mind, these are hard. So get started on them and come talk to me about them. I'd love to talk to as many of you as want to come talk to me about this. So determine whether this series so this series from 1 to infinity of n e to the minus n, whether that converges or diverges. Okay, so let's go back to your lovely morning yesterday in recitation. So we have these tests from section 8.3. We have the integral test. We have the comparison test. The integral test, of course, involves an integral. Comparison test involves having a known series that is comparable to the one that you're not sure about. And then there's the limit comparison test, which involves, again, having some known series that's comparable that you can compare in some other way. Now, what other tests do we have? These are all tests from section 8.3. Well, remember from section 8.2, we have this thing. If you know that a series converges, then you know its terms have to get closer and closer to 0. But that's no good. That's only useful if you know the series converges. We're trying to figure out if the series converges. But remember that there is the contrapositive of that statement. It says, if the limit of the terms does not exist, or the limit of the terms exists but it's not 0, then the series does not converge. That's the test for divergence. That's actually the simplest test to do. So let's knock that one off right away. Let's check to see what that test for divergence has to say about our series. This is from section 8.2. So the limit as n goes to infinity of a subscript n. That's the limit as n goes to infinity of n e to the minus n. So raise your hand if you have some wisdom about that limit. Two hands up. Sam, is your hand up? You're scratching your ear. What do you observe about this limit? I'd like to get some more hands in the air here. When n gets really big and huge, what's happening to n? Oh, it's getting really big and huge. What about e to the minus n? When n is really huge, what is e to the minus n doing? Jace? Yeah, so this is indeterminate form. Infinity times 0. You don't know which of those is going to win out. Something that's getting really big times something that's getting very close to 0. That doesn't mean, this doesn't really mean infinity times 0. So this should bring you back to the horrors of 2301. What do we do with an indeterminate limit like that? Alexander, your hand was briefly up. What was the name of the kind of, oh, Sam? Yeah, we use L'Hopital's rule. But we have to get this thing into one of the forms that we can use L'Hopital's rule for. This is not one of the forms. So what do we have to do? Hanukkah?
You've already used n over e to the positive.
Yeah. So this is the form infinity over infinity. So then we use L'Hopital's rule. So we can do the limit as n goes to infinity of the derivative of the top divided by the derivative of the bottom. And so that's the limit as n goes to infinity of 1 over e to the n. Okay, so let's get some new people involved here. What is this limit? So n is getting really big. So think to yourself, what is e to the n doing, and what is 1 over e to the n doing? Some new people here. Yeah. Yeah. So this limit is 0. So the limit of the terms of the series is 0. So what can we conclude? Marcy?
Converges?
No. We can't conclude that. So remember, the test for divergence is only a test for divergence. If the limit is not 0, then the series definitely does not converge. That's the contrapositive of this statement. If we know that the series does converge, if we know that, then we can say that the limit of the terms is 0. But the converse of that statement is not a valid theorem. Knowing that the limit of the terms is 0 does not guarantee that the series converges. Can anybody think of the quintessential series where the terms do get closer to 0 but the series does not converge?
Harmonic?
Yeah, just the series 1 over n. Those terms get it closer and closer to 0, but the series does not converge. Whereas the series 1 over n squared, those terms get closer and closer to 0, and the series does converge. So knowing that the limit of the terms is 0, well, it just means I don't know. It doesn't mean anything. So it means that the test for divergence is no help, because it's only helpful in the case where that limit is not 0. So it's not applicable. So what about other tests? The integral test. The comparison test. The limit comparison test. What do you think about these? Marcy?
I was going to say limit comparison test, but the top of that isn't a series.
Well, think about these comparison tests. Remember what you do in those to use those tests is you find some series that you know something about that's comparable to the series that you've got. Our series, it doesn't look like any series that we've seen before. You guys ever watch Wallace and Gromit?
Yep.
The Aardman? You know the one where they go to the moon? And they're sitting on the blanket, and he eats a bit of the moon, and what does he say? He says, "It's like no cheese I've ever tasted." So it's a good one. Yeah, so this is like no series we've ever seen before. So we don't have, it's like if you're trying to sell a house or buy a house, the realtors don't work that hard. They just go out and see what comparable houses sold for. If there are no comps, if there are no comparable houses in your area, then they have to work a lot harder to decide what to sell your house for, or if, how much you should pay. So these, we don't have a comparable series that we know anything about. We don't have a comparable series. So dang. The test for divergence is not applicable, and neither of these comparison tests is going to be useful because we can't think of a comparable series that we know something about. So that leaves us with the integral test. Now remember what the integral test is. The integral test is you have a function that's the associated function for the terms of your sequence. So you have the terms of your series are an, but you pretend that you think of the associated function f of x, and so and you consider this integral of f of x. If that integral converges, that series converges. If that integral diverges, then that series diverges. So our associated function is this: f of x equals x e to the minus x. And we need to consider the integral of that baby. But before we get to do that, we need to make sure that it's allowed in our exclusive club. We have to check. Is it continuous? Are the terms positive? Is it decreasing? If you look at the integral test, that's all part of the test. This is, how you finally do reach a conclusion. You find the integral and you see if it's convergent or divergent. But it's only useful information if you know that you have a function that's allowed to be playing. And those three things: continuous, positive, decreasing on the interval. So we need to know whether it's continuous on the interval 1 to infinity, whether it's positive on the interval 1 to infinity, and whether it's decreasing on the interval 1 to infinity. So who can help me out with this? How about continuity? Continuity of this function. Mary's nodding your head. You're right. Can you articulate why?
There's no discontinuities in like what the graph would be.
Yeah, you're right.
On that interval, I guess.
Well, Cassidy, you have a furrowed brow. What do you have to say about this?
Because our interval is all positive numbers and doesn't include zero, there's no place. Like she was saying that the graph, there would be any discontinuities on the graph because it starts at 1.
There are no discontinuities anywhere. E to the x is always continuous. So e to the minus x is always continuous. X is always continuous. So a product of continuous functions is also continuous. So yes. So it's a product of continuous functions. So you need to be able to articulate sort of why. How about this? Are our y values positive on this interval? Brandon, you're vigorously nodding your head. You're right. Sorry, you were nodding. I saw you. So it is positive, but can you articulate why?
Not likely.
Yeah. Too slow. Somebody else. Kinsey.
X is always positive, and e to the negative x is always positive.
Yeah, remember e to anything is always positive. The graph of e to the x lives above the y-axis, above the x-axis. So e to the 15 tan x minus secant squared of ln of x, doesn't matter what you put up there in the exponent, e to anything is always positive. So this is positive times a positive. So it's positive. Yes. What about decreasing? Is our function decreasing? Silver, you're being very quiet. What do you have to say about the decreasing question?
It is decreasing.
You're right. Can you articulate why?
I converted it to x over e to the x, and e to the x gets bigger faster than x gets bigger.
Eventually, but always? I mean, it seems like it's probably decreasing, but what's a way of really being sure about this?
If we take the derivative and it's always negative on that interval.
Right. We investigate f prime. If f prime is always negative, then f is always decreasing. So let's investigate f prime of x, which is the derivative of x e to the minus x. And so by the product rule, I take the derivative of the first times the second plus the first times the derivative of the second. And so that's 1 minus x times e to the minus x. Oh, that's not always positive. I mean, e to the minus x is always positive, but this can change sign. This changes sign. Well, okay, it changes sign at x equals 1. Let's be thorough about this, just because it's been a while since you did this. Let's make a sign chart for f prime of x, which is 1 minus x e to the minus x. So there's going to be one critical number, which is x equals 1. At that place, f prime equals 0. And then out here, well, we have, let's just use a sample. Let's use x equals 2. So f prime of 2 is going to be 1 minus 2 times e to the minus 2. So that's a negative times a positive, so that's negative. So that means out here, f prime is negative. Over here, let's do a sample x equals 0. So f prime at 0 would be 1 minus 0 times e to the minus 0. So that's 1 times 1. That's positive. So f prime is positive out here. So because f prime is negative, that tells us that we have the following behavior of f. F is decreasing to the right of x equals 1. Right at x equals 1, f has a horizontal tangent. And then because f prime equals 0 at that x value. Over here, f is increasing. So remember from Calc 1, using the derivative is a little bit tricky. The derivative only guarantees that f is decreasing for x greater than 1. But in fact, we can say that f is, we can say more than the first derivative tells us. F is decreasing on the half open interval, x greater than or equal to 1. Why? Because at x equals 1, there's a max. And then the graph is going down. So basically, on this whole interval, anytime you move to the right, the graph goes down. So even though the first derivative test only told us f is decreasing for x greater than 1, we can actually say that f is decreasing on that whole interval. So this is one example, and we haven't really even started the meat of the problem. We've just tried some stuff that either didn't help us, or we've focused on what our approach is going to be, and then we're making sure that we have our ducks in a row that we're allowed to do this, and now we're going to do it. So now we're going to do the integral from 1 to infinity, and this is x equals 1 of f of x. So that's the limit as b goes to infinity of the integral from 1 to b of f of x. Because that's what we mean by an improper integral. And what does that mean? Well, that means we're going to do this. We're going to do the indefinite integral of x e to the minus x, and then we're going to evaluate it from 1 to b. So this is the fundamental theorem of calculus. Now remember what I did in Calc 1. I would often break off and do the indefinite integral details off to the side. So I'm going to do that here. So we have this indefinite integral of x e to the minus x. So that's the thing that we're going to do. Now we're going to use integration by parts. So our f, let's call this our g, is going to be x, and our h prime is going to be e to the minus x. So then I have to take the derivative of g, so g prime equals 1, and h is going to be an antiderivative of that. So that's going to be e to the minus x over minus 1. So in other words, minus e to the minus x. And remember what we do in integration by parts. We take the product of these, and then we subtract the integral of these. So that's going to be x times minus e to the minus x minus the integral of 1 times minus e to the minus x. So let's clean that up. That's minus x e to the minus x, and then we have plus the integral of e to the minus x. Well, that integral is minus e to the minus x. So I end up with minus x plus 1 e to the minus x. So all of that goes here. So this is what we get. We end up with a limit as b goes to infinity of that stuff minus x plus 1 e to the minus x, evaluated from 1 to b. This is a mammoth problem. So how does that look? Well, let's see. We have to do all this with a b in there, minus b plus 1 e to the minus b, and then subtract all that stuff with a 1 in there. But the subtraction is going to get killed by that minus sign, so we're going to have plus 1 plus 1 e to the minus 1. All right, I'm going to bring the e to the b down to the bottom. And also, I'm going to break this up into two terms. So I'm going to have minus b over e to the b, and minus 1 over e to the b, and then plus 2 over e. Now remember, you can break limits up if you know that the pieces that you get are finite limits. So we're going to say, we're not sure, this is contingent. Can we do this? Limit as b goes to infinity of minus b over e to the b minus the limit as b goes to infinity of 1 over e to the b plus the limit as b goes to infinity of 2 over e. Oh, well, we did that limit a while ago. We did that limit with L'Hopital's rule. Oh, actually, I should put the minus out front. This limit we did with L'Hopital, this is 0. And this limit we can see is 0. And this limit is 2 to the e. And so the final value of the limit is 2 to the e. 2 over e. Look at that. The limit exists. It's a finite number. So the conclusion is since the integral of f of x is 2 over e, we conclude that the series converges by the integral test. And I should write the function in, x e to the minus x dx. Since that integral equals that, we conclude that the series n e to the minus n converges. Now, what's its value? Well, we don't know. We don't know if it's not going to be that number. But we know that it converges to some number by the integral test. Meaning part 3 looks like I'm not going to get to. I'm going to tell you what it would have been. It would have been example 4. We know that this series diverges. Question is, so that means if that series the limit is infinite, diverges to infinity. Question is, how fast? Well, so can use a graph that the partial sums, so SK would be 1 plus 1/2 plus 1/3 plus 1 over k. So that would be the sum as n goes from 1 to k of 1 over k. It turns out, if you, the interesting thing is if you use a graph of 1 over x, you can show that this is less than or equal to 1 plus ln of k. So this is using a graph. Yeah.
The term of that series should be 1 over n.
Oh yeah, 1 over n. So we can use this to estimate, what if we don't add up the whole series? So what if we just add up a whole bunch of terms, like say 1,000,000? S of 1,000,000. That means it's going to add up 1,000,000 of these terms. Well, that's going to be 1 plus ln of 1,000,000. That's going to be really huge, like 15. Add up 1,000,000 terms of that sequence, and they only add up to 15. Okay, let's add more. Let's add 1 billion. Okay, that's going to be huge, and it is. It's like 22. Pretty slow growth. So this series, it never stops growing. If you want it to be, you want to have the series add up to a quadrillion. Well, if you add up enough terms, it'll eventually get to a quadrillion. But you're going to have to add up a lot of them, because if I add up 1 billion terms, I've only gotten to 22 as the series. So it's pretty amazing how slow this grows. Okay, thank you all.